suppose that we have a second order system that looks like this, okay? So you can see these second order systems in many different applications, such as in the RLC circuit or in certain mechanical systems like something here, okay? So if you want to look at the specifics of this, right? So this is considering a mechanical system where you apply a force on this mass in this direction as the input, x of t, and the output is the displacement of this vehicle, okay? So, the effective force in this direction, right, is the mass times the acceleration of this object. And this is equal to the force applied in this direction, which is x of t, a force applied by the spring that pulls this back, right, which is equal to minus kyt because it's in this direction, and also this is called a dash pot, or you can just consider this as a damping system. As a damper that sort of restricts the motion of the vehicle in that direction. So this also applies a force that is proportional to the speed of the object in that direction, okay? So for this mechanical system, right, you also get a second order differential equation similar to this, right? So this is just an example of, where you would encounter such a second order system, okay? Now, for this second order system, we can look at its frequency response. So we can obtain the frequency response by taking the Fourier transform on both sides, okay, and then moving things around to get the ratio of the transform of y over the transform of x, right? So if you do that, okay, so we've showed all these derivations before, so I'm not going to go through the details of derivation, but just to look at how to visualize these types of frequency responses that take on this form, okay? So anyway, if you take the Fourier transform on both sides, move things around, you will get a frequency response that looks like this, okay? All right, so for this system, I can write it as omega n squared over, okay. So here we have a quadratic form in the denominator. So I can actually split this into j omega minus c1 times j omega minus c2, okay? And we all know how to find the roots, C1 and C2, of this quadratic equation here. All right. So here, C1 is minus zeta omega n plus omega n square root zeta squared minus 1. And C2 is minus zeta omega n minus omega n square root zeta squared minus 1. Okay. Now we can split into two cases here. One is for C1 equal to C2, and the other is for C1 not equal to C2. Okay. So this actually corresponds to the case where zeta is equal to 1 or not equal to 1. Okay. So when zeta is not equal to 1, then this term would be non-zero, and C1 would not be equal to C2. Okay. So for zeta not equal to 1, C1 and C2 are not equal. Okay. So what happens when, what can you do when they are not equal? So when they are not equal, you can use the partial fraction expansion to split them into two terms. Okay. And that will give you something that looks like this. Okay. So when C1 is not equal to C2, we can use the partial fraction expansion technique to split this into these two terms here. And it just so happens that the value in the numerator here is, is equal to m and minus m here, where m is equal to this. Okay. So once you are able to write the frequency response in this form, right, we know immediately what is the inverse transform of a response like this. Okay. So the inverse transform of this is a decaying exponential. Right. So this gives you a response h of t that is equal to m e to the c1t minus e to the c2t u of t. Okay? Or if you plug in all the values, you get omega n over 2 square root zeta square minus 1 e to the minus zeta omega n plus omega n square root zeta square minus 1 t minus e to the minus zeta omega n minus omega n square root zeta square minus 1 t u of t. Now similarly, when zeta is equal to 1, when zeta is equal to 1, the second term is 0, so C1 becomes equal to C2, okay? So when zeta is equal to 1, C1 is equal to C2 equal to minus omega n, right? And therefore, the frequency response takes on this form with the square in the denominator. So we learned before that when you have the square in the denominator, you need to apply some the differentiation property to help you find the inverse transform. And this is the outcome of that. Okay? Now, regardless of whether C1 is equal to C2 or not, you can see that the impulse response here is actually a function of omega n times t. Okay? So the impulse response is a function of omega n times t. Right? So if you multiply t inside, you have omega nt here, omega nt here, and also here and here. Okay? Or if you look at the case where zeta is equal to 1, you can also see that it's a function of omega n times t. Right? But if you look at the frequency response, which looks like this, it's actually a function of omega over omega n. So this shows that the time and the frequency domain has an opposite relationship with omega n, right? So in fact, if you increase omega n, right? If you increase omega n, then the time domain signal will actually vary faster with time, whereas the frequency domain will vary slower with omega. Okay. Now, vice versa, if you choose a smaller value of omega n, then your frequency domain will vary faster over the frequencies, whereas the time domain will vary slower. Okay, so there's always this opposite, behavior in the time and frequency scaling. Okay, so you can see that h of t is a function of omega nt, and this frequency response is a function of omega over omega n. So there's always this opposite scaling with respect to omega n in both in the time and frequency domain. Okay. Now, suppose we look into this equation more carefully. Okay. So if you look at this equation here, right, we actually have two exponentials, right, that are that only differ by a minus sign here in the exponent. All right. Now, if zeta is equal to 1, okay. So if zeta is equal to 1, we get a signal like this, okay, which just decays smoothly over time. Okay. But if zeta is less than 1, then zeta squared minus 1 is negative. So the square root of a negative value gives you a complex number, right? So if zeta is less than 1, square root of a negative value gives you a complex number, right? An imaginary number, okay? So when you have an imaginary number, let's say you have this j times omega n times t, then this part of the exponential gives you a sinusoid, okay? So when zeta is less than 1, this part gives you a sinusoid. But then what does this part give you? All right, this part gives you a decaying exponential. All right, so as time t increases, this is a decaying exponential. So we have a sinusoid multiplied by a decaying exponential. So we basically have a sinusoid that oscillates less and less as time goes on. Okay? Right. So this factor zeta here we call the damping ratio. And this omega n here we call the undamped natural frequency. Okay? Because this zeta determines like how fast this oscillation decays over time. And this omega n is the frequency of the oscillation when there is no damping. Okay? So in particular, when there's no damping, meaning that when zeta is equal to 0, you have just minus j omega nt, which means that you have a pure sinusoid at frequency omega n. Okay, so omega n is this undamped natural frequency because it's the frequency when there is no damping. Right. So as I just mentioned, if zeta is between 0 and 1, right, you have a frequency response that is basically a sinusoid. Right? This sine is obtained by Euler's relation when you combine these two complex exponentials. Okay? So you basically have a sinusoid at frequency equal to this that decays over time due to this decaying exponential. Okay? And this is called a underdamped system. Now, when zeta is greater than 1, then both C1 and C2 are real and negative. Okay? So when zeta is greater than 1, then these two are basically just two decaying exponentials, right? So there is no oscillation in the signal. And in this case, we say that we have an overdamped system. Okay. So for a underdamped system, we have this damped oscillatory behavior. Okay. And for the overdamped system, we do not. Okay. And zeta equal to 1 is this critical point in between under and overdamped. So you can visualize what this looks like. Okay. So this is the impulse response, and this is the step response. Okay. So if you look at these curves here, right, for 0.1 up to 0.7, right, which are underdamped systems, okay, you see these, oscillatory behaviors, okay, that gradually decays over time, right? But for zeta equal to 1.5, which is an overdamped system, you do not see an oscillatory behavior. In fact, it decreases smoothly over time. Okay? Now, in the step response, right, which is the integral of the impulse response, an underdamped system, right, by integrating this, an underdamped system will give you a step response that overshoots, quite significantly, especially when zeta is small, okay? But for overdamped systems, they do not oscillate and do not overshoot, but sometimes it may take a longer time for it to reach the desired gain that you want. Okay? So for underdamped systems, you have this overshooting plus ringing behavior. Okay? Okay. Now let's look at the frequency domain in terms of this log magnitude or the Bode plot. Okay. Okay. All right. So suppose you want to, draw out this Bode plot of this second order system. All right. So you first take 20 log of the magnitude of the response. All right. So if you plug, right, if you take this, okay, and plug it inside, right, taking the magnitude of this basically requires you to compute the square of the real part plus the square of the imaginary part, right? So if you do that, okay, then you will get a log magnitude that takes on this form here, okay? Now, similar to the first order system, we want to be able to approximately observe the behavior without actually calculating the specific values at every frequency, okay? So again, we look at the case where omega is, very small and when omega is very large. And in this case, we compare with this omega n here, okay? So when omega is much smaller than omega n, right, meaning that this ratio, both of these ratios are close to 0, then this is dominated by this 1, and log 1 is 0, okay? So again, at low frequency, the log magnitude is approximated by a 0 dB line, which is this line here. Now, at high frequency, when omega is much greater than omega n, this means that these values are very large, okay? But since this is to the power 4, whereas this is only squared, therefore this term also dominates this term. So when omega is much greater than omega n, we eventually need only to look at this term, which is omega over omega n to the power 4. You bring the 4 outside to get minus 40 log 10 omega, minus, canceled out with the minus here, becoming a plus, 40 log 10 omega n. Okay? So what this gives us is a linear equation with respect to the logarithmic scale of omega. So for every decade increase in the frequency, the gain decreases by 40 dB. Okay? So at high frequency, we have a 40 dB per decade line, okay, instead of the 20 dB per decade line for the first order system. All right. So at low frequency, the asymptote is the 0 dB line. At high frequency, this is the 40 dB per decade asymptote. Okay? And we have a break frequency at omega n. Okay. So if you compare with the first order system, right, instead of having 0 dB and then a 20 dB per decade slope after the break frequency, we now have a 40 dB slope. Okay? So we now have a 40 dB slope. Okay. Now, another thing to notice is that when you look at these two asymptotes actually does not depend on the value zeta. Okay, does not depend on the damping ratio, right? It only depends on omega n. Okay, and in fact, if you compare the solid lines here for different values of zeta and the two approximate lines that we get, you can see that there is a larger and larger discrepancy as zeta, becomes smaller and smaller, right? In fact, there is this peak here. There's this peak here around close to omega n, not exactly omega n, but there's a peak here close to omega n that becomes larger and larger as zeta becomes smaller, right? So we observe a peak at some frequency omega max. Okay? And what is this omega max value? Right, you can just take the derivative of this, right, and set it to 0, and you can find the extreme value to be omega n times square root 1 minus 2 zeta squared. Okay. Right. So what does this peak imply here? Right. So this peak implies that the frequency response of the filter, right, the gain that is imposed on the input signal has a large value at a narrow bandwidth around omega n. Okay. So if you pick a system with a small value of zeta, then it will give you a very large gain for signal components around the frequency omega n. Okay. So sometimes this is desirable, sometimes it is not. Okay. So it may be desirable if you want to construct a filter that lets through very narrow, very specific, frequency signals. Okay. And this will allow you to do that if that is what you want. Okay. Now we can also obtain this asymptotic studies for the phase as well. Right? So in this case, the phase is minus arctangent of this ratio here, that you can also approximate as 0 when omega is small, as minus pi when omega is large, and the line connecting the two. Okay? And this is the line that you get. But you can also see that there is a larger and larger discrepancy, if you have a smaller and smaller damping ratio. Okay. All right. So you just need to be aware that, if you have a system with a small damping ratio, then you have to be aware that this asymptotic line that you're using to study the behavior may not be so accurate, right? You need to sort of compensate for this if you're considering such a system. Okay. Now, why do we look at these second order systems so carefully? Right? So the reason is that the first order systems can actually serve as the basic building blocks for more complex systems, okay, that can be described by these linear constant coefficient differential equations. Okay. Now, what do I mean by that? All right. So what we know right now is the following. Okay. So what we know right now is what the this log magnitude and phase would look like when the frequency response when the frequency response looks something like this, which is a second order system, or when the frequency response looks something like this. Okay. So with these two, right, I can immediately get the Bode plot for systems like this and systems like this, because this is just the reciprocal of the first order system, and this is just the reciprocal of the second order system. Okay? Right. So suppose that you want to find the log magnitude of this system here. Right? You can actually compute minus 20 log of a system with frequency response 1 over h. And if you plug h inside here, 1 over h is actually the frequency response of the first order system we obtained before. Okay? So the log magnitude of this system is just minus the log magnitude of a first order system. Okay. So similarly, the log magnitude of this system here, right, if you plug this inside, is just minus the log magnitude of the second order system that we just looked at. Okay? So knowing how to analyze the Bode plot for the first and second order system, we know how to look at the behavior of their a reciprocal system. And it's also easy to find the Bode plot for this constant gain system, right? Because if you just plug this in, right, the log magnitude is also just a constant, right? 20 log k, and the phase is either 0 or pi, depending on whether k is positive or negative. Okay. So with these basic elements, we can then analyze more complex cases. Okay. So let's look at two examples here.